you'd use a design automation tool, fill the blocks in the GUI, and have it do that for you, rather than you trying to figure out how to write that module template. It says keep the number of FPGA gates at 30 to 80 PFU per block. PFU is a programmable function unit, which is another name for configurable logic block. What they're saying is don't try and put too much logic into one module. Take a look at the number of equivalent gates it would take to implement it, and split those into separate modules if necessary. State encoding methodologies for finite state machines. Okay, so you're going to have to pick some encoding of the states for your finite state machine. And they list some binary coding, gray coding, one-hot encoding, so you have different options available to you. It's interesting here, it says states with binary or gray coded states have a minimal number of flip-flops and wide combinatorial functions. If I have a finite state machine with 7 states, it's going to require 3 flip-flops if it's fully encoded. I'm using binary encoding or gray code. If I go to one-hot encoding, it will require 7 registers. Now, in the configurable logic blocks we looked at so far, you got 2 registers per configurable logic block. So if I am going to use the one-hot encoded, I need 7 of them. I'm going to require 4 configurable logic blocks to implement that one-hot encoded finite state machine. I would only need 2 configurable logic blocks if I use one of the full encoded. It says, however, most FPGAs have many flip-flops and relatively narrow combinational function generators, LUTs. Those LUTs are rather small, so that means you can't implement very sophisticated binary expressions, Boolean expressions in one configurable logic block. It says, on the other hand, one-hot encoded machines represent each state with 1 flip-flop. It decreases the width of the combinational logic, which matches well with FPGA architectures. Notice the next. For large and complex state machines, one-hot encoding is usually the preferred method. For small state machines, use the binary or gray code encoding. That's what Lattice recommends for their FPGAs. So if you have a large complex state machine, it's got 30 or 40 states in it, go with one-hot encoding. If you've got one that's only got 5 or 6 states, go with the binary or gray code encoding. That's what they're recommending. Again, design before coding, read the synthesis guidelines before you write your first line of code. This is something I wanted to show you. They're talking about for Verilog providing explicit state values. The question is, how would you tell the synthesizer you want one-hot encoding or some other encoding method for your finite state machines? Well, there's 2 ways. One is you'll find that it is a synthesizer option. That when you set up your synthesizer to synthesize a design, you come to a phase where you say, I want my finite state machines encoded with one-hot encoding or binary encoding or whatever. Another way you could do it is in your Verilog code, What is that? Synthesis directive. And notice where it goes. Next to the declaration. When we talked about encoding finite state machines, we always had a register declared that kept track of what state I was in. That's where that synthesis directive goes. And then the value here could be, they tell you, sequential, one hot gray, or safe. I'm not sure what sequential and safe are, but the point being, I can specify here in this synthesis directive how I want my finite state machine encoded. So on the next page, they show an example. And they don't use the synthesis directive here. But this statement right here, which you can't read that well, is one of the ways that we recommended that you code the finite state machine. You have one always block that updates your state. And then you have another block that determines what your next state should be and your output should be. This second block does not have the clock in it. The first always block does, so your state transitions take place on specified clock edges. This tells you that, as you know, in all finite state machines, there has to be an initial state. You have to be in that initial state before you apply your first input. So the question is, how do you initialize it? Well, it turns out that in Lattice Semiconductor FPGA devices, there is a global set reset, GSR, that is pulsed on power up when you first apply power to the FPGA. So you can use that to initialize it. And then they show you here in Verilog coding where your state information has a default, and down here where they use the synthesis directive full case so that you don't have to have the default statement. The synthesis parallel case is if each of these are known to be mutually exclusive, which of course they are in finite state machines. You can only be in one state at a given time. You can wind up with simpler, faster code by using the synthesis directive parallel case. This shows the advantage of pipelining, and this is somewhat tied to the idea of registering the output of modules. This shows a particular design, and between this register and this register, there are 3 combinational logic blocks. After you get an output here, you have to go through propagation delay in this block, and this block before you can start the setup time on this register. And that means that you're going to have a clock with a relatively long period so that the output here, until you satisfy the setup time period here, the period is adjusted so that 2 successive, let's say, leading clock edges are far enough apart in time so that you don't run into timing problems. if you insert registers in between these combinational logic blocks, it turns out that you can have a much faster clock. So if you're having trouble meeting a timing constraint, what you may have to do is pipeline your design. And all pipelining means is I insert registers between the combinational logic blocks. The reason why the pipelining turns out giving you a faster design is, let's suppose I've got a number of data elements that I'm going to be running through this particular data path. So I apply the first data element. On the clock edge, it gets stored in that output. That combinational logic block can now work on it and provide it to the next register. Now you notice these two registers are clocked with the same clock. So what happens on the next clock? Well, the data that was processed by that block is now stored here. That frees up that combinational block to now start working on the second data element that you're inputting. What happens on the next clock? Well, the data that was processed in here can now be processed by this block. The new data that was stored here is now been processed here. It's going to get stored in this register. And that frees up this block to work on the third data element coming in. So different stages in this pipeline are working on different data inputs. My clock period now only has to worry about going through the propagation delay of one block, not three, so I can have a faster clock. So this is a much faster design and may help you meet timing constraints. Comparing if, then else, and case statements. The if, then, else statement generates priority encoded logic, whereas the case statement implements balanced logic. Let me show you what they mean by priority encoded logic. I'm just going to put a number in here. For reference purposes. First thing checked is item number 1 here. The next thing checked is 2. The last thing checked is 3. I'm going to put an else if. This is the type of circuitry generated. These are supposed to be multiplexers, incidentally, not ALUs. You have to go through the propagation delay of all of those to get an output. It's priority encoded because this is the most important thing that you check, so that's on the output. So if that's true, it immediately goes to Y. This is the next highest priority, so you got to compare that against these, and so on. So this is what I mean by priority encoded logic. The case statement tends to balance this out, where you've got, instead of different layers of individual muxes, you have multiple muxes per layer. You have fewer layers, lower propagation delay with casing. That said, here's what they recommend. If each output is indeed dependent on all of the inputs, it's better to use a case statement than an if-then-else statement. So you have your choice of encoding it either way, and you're going to get the same functional behavior. But they're recommending under this circumstances, you should be using a case statement. Here they're talking about latch inference. Here are ways that you can get latch inference. It says another way to avoid non-intentional latches is to check the synthesis tool outputs. The synthesizer is going to generate a report file, a log file, if you will. There will be warnings if you have latch inference. And what they're recommending, and why I put a star here, is you need to check the synthesis output file and see if you had any latch inference warnings. If you do, you need to go back to that code that produced the latch and modify it. So you need to check to make sure that you don't have latch inference issues. They do give a list here. They talk about using library components, second-party IP, and this is the type that Lattice provides: logic gates, slots, counters, flip-flops, latches, multiplexers, phase lock loops, boundary scan, and so on. Gated clocks. We talked about that before. If you have a free running clock that runs continuously, don't gate the clock. Instead, add the multiplexer in here and let your clock run all the time. And it shows down here how you would implement this particular circuit in Verilog. Just notice this mux requires or was generated by an if-then-else statement, and there's your if-then-else statement. We talked about that global set reset function. This shows you the code on how you can do this. Here I want a reset to be my reset signal that goes throughout the FPGA to initialize different circuitry. That's how you instantiate it. It's a library component. Its name is GSR, all uppercase, so I just instantiated, connect by name to GSR, the reset signal I want to use. This will generate a pulse on RST when the FPGA powers up. So there's a simple way that you can get a pulse to initialize your design. Inferring bidirectional ports. Particular circuit that we're looking at here for this bidirectional port. See, B is, gotta look at, B is active zone. Okay, so I've got a pair of tri-state buffers here. This is a bidirectional port. If the direction line is a logic 1, data will flow from A to B, because that's the tri-state buffer that's going to be activated. This one will be in a high impedance state. On the other hand, if DIR is low, this lower tri-state buffer is activated, and this one is in the high impedance state, so data can flow from B to A. So that's how you infer it. Could I have instantiated those?
No.
Yes.
And Verilog provides you gate primitives.
Yes.
This would be a if buff 1, if buff 0, and then I would connect them together through the port list. That would be instantiation. That's how you infer it, with two if-then-else statements. Notice that if the direction is a logic 1, B equals A, otherwise it's the high impedance state. And if DIR is low, A equals B, otherwise you're in the high impedance state. Another example of inference versus instantiation. Okay, let's take a 10-minute break.